5 times the 2 seconds, you get negative 10. So I have a positive 90 meter displacement, I have a negative 10 meter displacement, the total 80 meters. But if I'm looking at just the distance, I go 90 meters, then 10 meters, I go 100 meters. For the entire trip, what's my average velocity? Not average.
meters per second.
How'd you get 50?
15.
15? How'd you get that? For the entire trip of the 8 seconds.
Is that not what we used to find the difference?
We got 15, that was just for the trip, for the first 6 seconds. I'm talking for the entire time. All right, Jacob?
Is it 20? 20?
How'd you get 20?
Oh, wait.
You forgot something.
I did 30 and negative
8.
Oh, 10.
I was like, yeah.
10.
Average velocity.
All right, we can find it 2 different ways. I know average velocity if acceleration is constant, and it is. That's the uniform. This tells me that it's constant. I can take my initial velocity plus my final velocity, divide by 2. Again, this works only if acceleration is constant. And so I have 30 plus negative 10 divided by 2, which is 20 over 2, which is 10, and then don't forget the units. And it is positive. The other way I can do it, average velocity, and this is always true, regardless of the acceleration being constant or not, it's displacement divided by time. And I know that's 80 meters over 8 seconds, which is 10 meters per second. So this formula always works for average acceleration. This one works only if acceleration is constant. And we have a lot of constant acceleration problems. Questions here? All right, all this is well and good. I know what you're thinking. You're going, hey, the math was great. Can we do it with calculus? I'm gonna go, no, not for this course. The other question you're having is, what would this look like graphically? Well, let's look at that graph. I know that, let's just start out with a velocity versus time graph. I know I start at 30. So 10, 20, 30, negative 10, and we'll put that in meters per second. I'm starting here. I end up at 8 seconds here. I know my acceleration is constant, and I know acceleration is the slope of this. Since acceleration is constant, the slope of the velocity time graph has to be constant. Acceleration is slope of velocity versus time. And so that's what it looks like. Should be a straight line connecting the two. The cross of the x-axis at 6 seconds. Displacement, though. I should be able to get displacement off of this. Well, if I want to know how far I actually traveled in the positive direction, well, let's just take a look at that right triangle right there. What is the area of a triangle? Flashing back to geometry or elementary, I don't know when you do that stuff. It's been too long for me.
Area?
Area of a triangle.
Base times height divided by 2.
Yeah. So I got 1/2 base times height. My base for this triangle is 6 seconds. My height is 30 meters per second. So if I go through the math there, I get 90 meters. Hey, that's what we had over there. Now I look at this right triangle right here. It's another triangle, so 1/2 base times height. So that's 1/2 times my base now is, well, what is my base?
2 seconds.
What's my height? -10 meters per second. And we ended up with -10 meters. So we have one other rule here. We have area is the slope of the velocity time graph, but displacement is the area under velocity first time. Now I put under in quotation marks. This is math terminology. When you say the area under the curve, it's the area between the curve and the horizontal axis. So this is still considered under the curve. And in a similar vein, change in velocity is the area under acceleration first time. Questions before I read your mind one more time? Let's see if I get this one right. What you're thinking is, hey, constant acceleration problems are great, but what about non-constant acceleration? How do we deal with that? I'm glad you thought of it. Let's just start out with different colors. I'm going to start out with the position versus time graph. Probably looks familiar to some of you. It's completely above the horizontal axis before. I know that velocity is the slope of this. So first thing I would do, if I want to do a velocity versus time graph, is figure out where's the slope equal to 0. How do you deal with a slope of something which is not a straight line? And I think I mentioned this before, I mentioned it recently to some class. If I want to find the slope at this point right here, what I need to do is I draw a tangent line. A tangent line will just skirt the curve. There's a formal math definition that I'm not going to torture you with. It should just barely touch at that point right there. And so the slope at this point really is the slope of the tangent line. And I think I've asked this before. Who's had calculus? Or has had? Okay. I know this is repetition for you, just bear with it. So I'm finding the slope of the tangent line. Well, if I look at that slope, is that a positive or negative slope?
Negative.
Positive.
Most people call it positive. Where's the slope equal to 0? Pardon?
The t-axis?
The t at here?
Would it, if it was like just,
So you're fading off there, right? You said if it were straight.
like if it was just parallel to the
Oh,
t?
if it's parallel to the t-axis, so where on this curve would the tangent be parallel to the t-axis?
Nowhere.
No, it's somewhere. Jacob?
The bottom of the curve.
Yeah, down here
Yeah.
and
Top.
Top, yeah. So the tangent here, here, and here, it's 0. So that would be 0 there, 0 there, and 0 there. Obviously, our graph should be more than just 3 data points, so let's fill in the rest. I know it has to hit 0 there, there, and there. In between here and here, again, I'm not going to go from positive to negative or negative to positive without going through 0. Since I don't have 0 between these 2 points, it's all got to be the same. Is this a positive slope or a negative slope? It is a negative, so I'm going from here to here. What about over in this region?
Positive.
Now let's do the next one. If I were to do acceleration, I would rewrite, because it'd be really nice if I had one of those sliding boards. Where is the slope of this equal to 0?
Again, at the top and bottom.
Okay. There. And there. In this first region over here, in this region right here, is my slope positive or negative? Indeed. And it starts out at a steep slope, so it starts out negative. What about this middle region? Positive. And I know it has to hit 0 there. And in this last region? Negative. Hey, it's the upside down version of that. Yeah, let's go ahead and finish it. The first graph that I drew up there for position, what function is that? Yep. This is a cosine curve. This one,
Sine.
close,
Negative sign?
negative sign. And this one,
Negative cosine.
if I went down again, I would get, well, let's do the next one. What is this called? What's the slope of the acceleration versus time graph? Pardon?
Speed?
No.
Velocity?
No.
Displacement?
All right, imagine you're in a car. You're at a stoplight, it's red, your acceleration is 0, everything's good. So you're in a car, this is your head. The light turns to green, there's a car in front of you, light turns to green, and you slam on the gas pedal. So your head does this, but then, well actually, no, that's it. So you slam on the gas pedal and your head, because of inertia, will do this. What happened to your head? What is the word for it?
Jerk.
Yep. It's jerk. Then you realize the car in front of you that hadn't moved yet, so you slam your foot on the gas pedal. So basically your head does this, and then you slam on the brakes. Don't slam on the gas pedal. Slam on the brakes, so your head does this when you slam on the gas, and when you hit the brakes, your head does that. So what's happening to your head then? Besides perhaps whiplash. Jerk. No, we've already done the jerk. It's the next one. This is the slope of the jerk graph. First time. Oh, that was a clue. Snap. The graph of the snap first time graph. Come on, you all know what comes after snap.
Break.
Crackle.
Yep, crackle. And then? So we have position, velocity, acceleration, jerk, snap, crackle. Now, how official are these? If you're in elsewhere and you use this terminology, would they just look at you strangely, having no idea what you're talking about? Jerk is an American expression. There are other terms used in England, like jounce, or I have a list that I've written down. Jerk is an American term, snap, crackle, and pop, pretty American as well. It has been, snap, crackle, and pop has been used in 2 official journal articles, official referee journal articles, which is a necessary step in becoming accepted worldwide. So it's not there, snap, crackle, and pop are not internationally accepted, but if you're talking to American physicists and you mention snap, crackle, and pop, they know what you're talking about. All right, so anyway, so the pattern goes, and I keep putting these things down. Oh, I wrote that paste. There's the other one. So if you start with a cosine curve and do the slopes, you'll get a negative sign. If you do negative sign, slopes will do negative cosine. Negative cosine will get you sine. Sine will get you, well, cosine. So this one, if we did it more methodically, and let me move my axis some, it's 0 here, here, and here. My slope is positive, and then negative, that's a sine curve. If I did the slope of a sine curve, well, it's 0 here and here. My slope starts out positive, then it becomes negative, then positive again, so we get a cosine curve. So wherever you started the cycle, if this is my position graph, that's my velocity, acceleration, jerk, snap, crackle, pop, and so on. For those calculus students, the derivative with respect to whatever the variable is, the derivative of cosine is negative sine is derivative of that is that, and so forth. All right, questions in here? Onward. It's another one-dimensional problem. Ball's being thrown straight up. If the sign's straight up. All right, we have the big 5, displacement, initial velocity, final velocity, acceleration, and time. What are we given in the problem?
Initial velocity.
All right, I actually gave you initial speed. How do you want to express upwards?
Positive.
Pardon?
Positive.
Okay. Why? Was that Kevin who said positive?
Yeah.
So why is up positive? Everyone else? Pardon?
Because he said so.
Yep, absolutely. Because Kevin said so. So this is 20 meters per second. What other information is given to us in the problem? In terms of, because we need 3 things. Only one is given so far.
Acceleration.
Where's acceleration on this?
The force of gravity on Mars.
Ooh.
No.
All right, the spirit of what you're saying is right, on the wording, try the wording again.
The, what's it, G?
Okay.
The magnitude of the gravity?
All right,
Is it?
so this is, not everyone gets is picky about this, but I am. All right, gravity is a huge topic. We are gonna be looking at very tiny aspects of it. So when you just say, use the word gravity, that is a very huge topic, which covers so much more than we are possibly getting into. So let's be more specific. And the other problem is, there are three things that I have found in the past, students all call gravity, and even though they are all related, but very different. So,
Gravitational force?
pardon?
Gravitational force?
Gravitational force is not the part that we really, is our biggest concern right now. It's,
Gravitational pull.
that's a pull, force is a pull. Gravitational, what are we trying to find here?
Energy?
Whoa, no,
Acceleration.
acceleration, gravitational acceleration. All right, acceleration due to gravity as it's typically said. I don't know if you saw the sign in the lab room where it said, G is not gravity. Little g here is the symbol used for the acceleration due to gravity, or gravitational acceleration if you want to use fewer words. So, g is not a constant, little g is not a constant. Little g is the magnitude, going to something Robert said, it's the magnitude of the acceleration due to gravity. On Earth, on average, g Earth average is about 9.8 meters per second squared. In Winston-Salem, it is 9.798 meters per second squared. I think Rome is 9.8. I think Mexico City is 9.78, something like that. So it is, it is not a constant. It does depend upon where you are. Matter of fact, if we were doing